Erwin Schrödinger developed an equation and a model for the electron that predicts line spectra, and it incorporates this wave-particle duality and the resulting uncertainty surrounding the position of the electron. And this quantum mechanical model treats electrons like they're standing waves, so like a guitar string or a violin string. So if you've ever taken physics in high school, you've learned about standing waves, and we can relate the fundamental frequency and the various overtones to the principal quantum number n. So if you have a standing wave, you get a guitar string, for example, connected to 2 points, and you flick it, or you strum it, it'll oscillate back and forth, above and below. And the lowest energy vibration you can get is known as the fundamental. This is the lowest energy state, and this would correspond to an n of 1. The next highest energy level, so if you strum the string harder, is what's known as the first overtone. And this process can kind of continue on forever and ever. You strum harder, you get higher overtones. So I'll show you the next one, the n equals 3 level. And you can see even in this simple model with guitar strings that you end up with areas where the amplitude of these waves are 0, which is the height goes to the 0 point. And these points are called nodes. In every orbit other than the fundamental, you have nodes, and the number of nodes increases as you increase in your principal quantum number. So the n equals 2 level has a single node, the n equals 3 has 2 nodes, and so on. So solutions to Schrödinger's equation are called wave functions, and they allow you to work out the electron's probability density. So an electron's probability density is a 3-dimensional space where there is a chance of finding an electron. And if you have a higher density, there's a better likelihood of finding an electron, and a lower density is less likely to find an electron. And this is how Schrödinger incorporated the uncertainty in the position of an electron by treating it as a probability of finding that electron. And these areas of probability density are known as orbitals. So these orbitals are the new and improved version of the orbits that we learned about earlier. And just like the guitar strings that they're modeled on, these orbitals can have nodes. Now they can have areas of high density, of lower density, and nodes where there's 0 probability of finding an electron. And unlike orbits, these orbitals aren't simply circles around a nucleus. They have all sorts of strange shapes. So these orbitals can have very different strange shapes, and they're grouped into different types of orbitals. And they're known as S, P, D, or F orbitals. And they start very simply shaped with the s orbitals that are spheres. They get a little bit more complicated with the p orbitals that are kind of dumbbell shaped. We typically draw them like this. And they get considerably more complicated with the d orbitals. They're not just different orientations of the same shape, they actually have different shaped orbitals. Some of them look like this, almost like 2 overlapped dumbbells, and some of them look like this. Very strange. I'm not even going to attempt to draw the f orbitals. They're far more complicated, and I won't ask you to ever draw the f orbitals.